Welcome to this introduction of acid-base physiology. We'll look at how acids and bases function in the body, how we monitor their balance, and what we do with that information. Let's start with a review of some basic chemistry terms. First, we have acids. Acids are substances that release lots of hydrogen ions when they're dissolved in water. So these are your acids. Then we have bases. Bases are substances that release hydroxide ions, or these OH negative ions, when they're dissolved in water. So bases on this side. Now, if you know anything about chemistry, you know that the H plus and the OH negative like each other. They like to hang on to each other. So you could also think of bases as ions that will accept or cling on to the hydrogen ions. Then we have buffers. Buffers are molecules that can either donate hydrogen ions or accept hydrogen ions, so they can go back and forth between being an acid and a base. So they're one of the ways that the body balances the acid-base level in your blood. And then finally, a quick definition of pH. We use this to denote how acidic or basic a solution is. So a low pH is on the acidic side, and a high pH is on the base side. If you've ever wondered why low pH means lots of H ions, it's because that P actually equals 1 over those H ions. So if you have lots and lots of H ions, your P value will actually get smaller. Okay, let's make this specific to the human body. In the human body, the most common form of acid is called carbonic acid. But there are, of course, other kinds of acid, like hydrochloric acid in your stomach or lactic acid released by your muscles during exercise. In fact, the most common source of acid in your body is cellular metabolism, especially anaerobic metabolism, or those periods of metabolism without sufficient oxygen. Any type of cell injury or destruction or death will also release acidic byproducts into the body. And lastly, your lungs trap carbon dioxide, and that will also turn into an acid when dissolved in the water in your body. On the base side of the balance, the most common bases found within your body are different forms of bicarbonate. This is a negatively charged ion that readily accepts those hydrogen ions. Your pancreas produces most of the bases in your body, primarily to help with different forms of digestion. So it makes sense that in your intestines, you would find a lot of base. Also, your kidneys can reabsorb bicarbonate ions from your blood during the filtering process, so they also play a significant role in regulating the base level within your body. This chemical equation helps to demonstrate how both the lungs and the kidneys can affect the acid-base balance in your body. On this side, we have the lungs part of the equation, and on this side, we have the kidney part of the equation. So over here, we've got carbon dioxide and water. Obviously, your lungs are responsible for exhaling carbon dioxide into the environment. So if they, for whatever reason, hang on to too much carbon dioxide, that gets dissolved with water in your body and turns into, this is carbonic acid. Conversely, your kidneys, we just said, can filter this bicarbonate ion out of your blood and keep it in your body. It readily accepts hydrogen ions, and then together they can also form carbonic acid. So your body is constantly going back and forth between these two systems to maintain a normal acid-base balance in your body. Let's review these systems of acid-base balance one more time. You can think of it as 3 lines of defense against imbalance. The first line is just those chemical buffers. A lot of times, this is actually proteins in your blood. Proteins are such large molecules that they can easily accept a few stray protons or H+ ions whenever they need to. The second line of defense is your respiratory system. Remember that this controls the carbon dioxide levels in your blood and therefore the carbonic acid levels. And this takes seconds to minutes to respond. As a note, this one is instant. Then the third level is your kidneys or your renal function. And this controls the bicarbonate level in your blood. This takes hours or even days to start functioning. With the 3 of these systems working together, your body usually does a very good job of maintaining a normal acid-base balance within your blood. Let's do some visual examples to try to make this clearer. Let's use A's to represent acids and B's to represent bases. And we'll pretend that acid-base balance is a 1-to-1 equivalence. In real life, just to point out, it's not 1 acid to every 1 base, but we're going to use that for the purposes of illustration here today. So typically, your body has regulated the balance. We're good. Acids and bases equally balanced, no disruption within the body. However, sometimes this does malfunction. Sometimes the body enters a state we call acidosis. That simply means that the acid-base balance has been shifted over to that acidic side. There's 2 reasons this could happen. First, maybe there's too much acid building up in the body, whether that's too much carbon dioxide in the lungs or too much acidic byproduct from cellular metabolism or injury or death. The other possibility is that there's a normal level of acid in the body, but that for some reason the body has gotten rid of too much base. This might be something like kidney failure or some kind of chronic diarrhea. Remember, the base is controlled by the kidneys and the pancreas via the intestines. And the acid is controlled by the lungs and then cell metabolism. Okay, let's look at the opposite problem. When the balance in the body has shifted towards the base side, we call that alkalosis. Alkali is an old word for base. So that's where that name comes from. So one of the possible causes of alkalosis is that there's too much base in the body. For example, maybe somebody ate too many Tums. Tums are basically just bicarbonate. Or there could be the opposite problem. Maybe there's a normal level of base in the body, but there's also been a lack of acid. This might happen if somebody has an elevated respiratory rate, for example. So again, the lungs and cellular metabolism on the acid side, and the kidneys and the pancreas/intestines on the base side. When healthcare professionals need to monitor the acid-base balance in someone's body, we typically use what's called an arterial blood gas. It's also possible to sometimes use venous or capillary, but those are less common and less accurate. So today we will be focusing on the arterial version. We'll look at each of the components of the arterial blood gas and how we use them to interpret the status of the body in a minute. But let's first just talk about how we collect an arterial blood gas. As the name implies, this is an arterial blood draw. So there are some special considerations that come with drawing blood from an artery instead of a typical vein. The first is called the Allen test, and it's something we use if we are drawing blood from the radial artery in the forearm. This is the most common site used for these arterial blood draws. The challenge is that we have to occlude the blood flow through that artery while we're drawing it, and then for 5 to 15 minutes afterwards to prevent bleeding. And there are only two arteries that supply blood to the hand, the radial artery and the ulnar artery. They're also quite small, so it's easy for them to become occluded through disease or injury. So we do the Allen test to just make sure that blood flow to the hand will not be interrupted. What you do is you occlude both arteries using your fingers and ask the patient to make a tight fist. This forces all the blood out of the hand through the venous system. You then release the ulnar artery and allow the patient to open their hand again. As long as the ulnar artery is patent, blood will then return to the hand and the fingers will quickly turn pink again. If the ulnar artery is occluded, however, blocked off, the hand will stay pale and white until you also then release the radial artery. As a side note, blood draw from these arteries in the arm can be quite painful, so consider asking for some lidocaine if we have the time to allow it to work before the blood draw. The final thing that's very important to remember after using an artery to draw blood is that you have to hold pressure, or the artery will continue to bleed. This is a photograph of someone's arm after they had an arterial draw from the brachial artery, and nobody held pressure, and that blood just leaked into the entire arm, and you can see what a painful, swollen bruise that caused. The normal guidelines for holding pressure say 5 to 15 minutes. Be aware that you don't go longer than that 15 minutes because remember you are blocking blood flow through that artery. So the opposite problem is that some people will place a pressure bandage, walk away and forget about it. But then you're actually causing impaired blood flow to the limb, so make sure you are holding it just to that 5 to 15 minutes. Once you've drawn the ABG and you have your results back, these are the components that you'll typically see. First, the pH, then the PCO2, the bicarbonate level, the PO2, the O2 saturation, and sometimes you'll also receive a base excess. Let's look at each of these individual components in more detail. Remember that the pH is actually the amount of hydrogen ions in the blood, just the inverse of it. So the more hydrogen ions you have, the lower the P will go. The normal pH in the body is 7.35 to 7.45. Now, completely neutral is 7. So you can see that the body hangs out just a little bit on the alkalotic side, and we really don't have a whole lot of wiggle room there. Anything lower than 7.35 is considered acidotic, and anything greater than 7.45 is considered alkalotic. The PCO2 shows you the partial pressure of carbon dioxide in the blood. That just means how much carbon dioxide is actually dissolved into the blood. The normal values here are 35 millimeters of mercury to 45 milliliters of mercury. Now this should look familiar because remember the pH was 7.35 to 7.45, so that's nice. Just one set of numbers to remember. Remember that in our chemical equation back at the beginning, carbon dioxide plus water equals carbonic acid. So when you're analyzing a blood gas, it's useful to think of carbon dioxide as an acid. Therefore, anything lower than 35 would actually be alkalotic because you don't have enough acid. And anything greater than 45 would be acidotic. Also remember that this is largely controlled by the lungs. So think of this as the respiratory indicator. All right, next, let's look at the level of bicarbonate. The normal value here does depend a little bit on which lab you're talking to, which lab values book you're reading, but we'll use 22 to 28 as a nice broad normal range. Now remember, bicarbonate is mostly a base. So if there's too much of it, if your value is greater than 28, the body would be alkalotic. On the other hand, if there's not enough of it, the body will be acidotic. Again, remember that this bicarbonate level is controlled mainly by the kidneys and the intestines. So we call this our metabolic indicator. These three values, the pH, the PCO2, and the bicarbonate, are the most important values we're going to look at in the blood gas. But there are still a few more that can give us some helpful clues. The PO2 is again that partial pressure of oxygen this time dissolved in the blood. Don't get this confused with the pulse ox. That's something separate. The partial pressure of oxygen is measured in millimeters of mercury, not a percentage. The normal values for adults, typically 80 to 100 millimeters of mercury. For kids, we do usually see it a little higher, 90 to 100 milliliters of mercury. Although this 100 number is our normal max, if someone takes a lot of big, deep breaths, they can actually go over 100. Now, this doesn't have any direct effect on the acid-base balance in your body, but it can give us some nice clues as to the respiratory status of the patient. The oxygen saturation is what we commonly call someone's pulse ox. And this is the percent of your hemoglobin that is full or saturated with the oxygen. The nice thing about oxygen saturation is that we can measure it indirectly with the use of that red light being transmitted through a patient's skin. That's why we use this rather than the partial pressure of oxygen as routine part of vital signs for patients. The normal values here, for adults, we usually like 92 to 100%. Again, kids, we usually see a little higher, 93, maybe even 94 to 100%. Now, because it is a percentage saturation, you can never go higher than 100. It's not going to happen. The final piece of information we might see in an ABG is called the base excess. This is calculated, not actually measured. so we don't always need it, but sometimes it can help us differentiate between a problem with the metabolic system or a problem with the respiratory system. The normal value is -2 to +2. -2 means there's not enough base, and +2 means there's too much base. So base excess is a funny name since sometimes we're actually saying it's not enough. Now, if you're not given a base excess value in a practice problem or in real life, don't freak out. We can still figure out what's going on. And in fact, you'll see that in most of the practice problems we do together, the base excess has just been left off since we actually didn't need that information. Okay, now that we've looked at all those components separately, let's start putting them together to try to help you make sense of all this. So here's an example of a patient and the corresponding blood gas. We have a 9-year-old child with a history of asthma who's audibly wheezing and hasn't slept well. Usually that means there's an asthma attack. The patient is having trouble breathing. We also see that the patient is sitting upright and using accessory muscles to breathe. Again, more clues that something is wrong with the respiratory system. So we get the blood gas, and here's our results. For the pH, 7.29. We can remember that 7.35 to 7.45 is normal, so 7.29 will be acidotic. The PCO2 is 55. Again, normal was 35 to 45, so 55 is also acidotic. Remember to think of CO2 as an acid. We have too much acid, it's acidotic. The PO2 is 69 millimeters of mercury. Remember that normal for kids was 90 to 100. So this is low hypoxia. Again, doesn't have a direct effect on the acid-base balance, but is another clue that my patient isn't breathing correctly. And then the last one, the bicarb HCO3, the value is 23. That's normal. So nothing's wrong with the base levels in my body. So what we have here is an acidotic situation, and because it's the CO2 level that's out of whack, and we said that was our respiratory indicator, I know that this is called respiratory acidosis. Whenever you see a blood gas, that's what you need to decide. Is it acidosis or alkalosis? And is it a respiratory problem or a metabolic problem? If just looking at the values gets you a little mixed up, let me show you an easy way to set yourself up. First, start by drawing your own little version of tic-tac-toe. This middle section here will be normal. This left side will be acidotic, and the right side will be alkalotic. If it helps you remember, you can even write in your normal values. So for example, I know that my pH needs to be 7.35 to 7.45. I know my bicarbonate needs to be 22 to 28. Now the tricky one is the PCO2, right? The acidotic values will actually be 45 plus, and the alkalotic values will be less than 35. So be careful here. We have to kind of turn our CO2 backwards to make it work on our tic-tac-toe board. Okay, let's do this problem one more time using tic-tac-toe. We start with our pH. So 7.29 we said was acidotic. We're going to write pH in the acidotic column. Then our PCO2 was also acidotic. PCO2 goes in the acidotic column. And then our bicarbonate is normal, so that goes in the normal column. So I can see that the column where I actually got my tic-tac-toe is right here in the acidotic column, and it's the PCO2 that's over here on the same side as the pH. Again, that's my respiratory indicator, so I know that this really is respiratory acidosis. Now that example was fairly straightforward, but you know that your body is always trying to keep you in a state of homeostasis. So sometimes your body has actually started to compensate for the problem. This is where opposite systems pull in opposite directions. So, for example, maybe your respiratory system is pulling towards the acidic side, but your metabolic system will try to compensate by pulling back towards the alkalotic side, and so your pH might actually end up being normal because of these warring forces. Of course, don't forget that your respiratory system could pull towards the alkalotic side and your metabolic system could pull towards the acidotic side as well. It can go either direction. So compensation, we always see the opposite systems in opposite directions. We do have two levels of compensation though. Partial compensation is where the compensation process has started, but the pH is still abnormal. Full compensation or complete compensation is where the compensation has actually reached a point where the pH is back to normal, but remember that your two systems will still be abnormal. So let's take a look at some compensation examples. In this example, we have a 12-year-old patient with diabetes who presents with Kussmaul respirations. Kussmaul respirations are those big, deep, fast respirations. So even before reading the blood gas, I know that that patient is exhaling a lot of carbon dioxide. I expect the PCO2 to be low. So let's draw our tic-tac-toe board and see what happens. Here's the acid side and the alkalotic side, normal in the middle. Okay. First, let's start with the pH. pH 7.15. Again, remember that your normal values are 7.35 to 7.45. So 7.15 is acidotic. pH comes over here in this column. Next, our PCO2. PCO2, remember normal value is 35 to 45, and our value is 12. Low PCO2. Think of that CO2 as an acid. Low acid. So our PCO2 ends up over here on the alkalotic side. Our PO2 is a little bit high. Again, remember it has no direct connection to the acid-base balance, but it does in fact have a connection to these big, deep, fast breaths. Okay, finally, our bicarb, our HCO3, is only 8 milliequivalents per liter. Remember, our normal low was 22. So low bicarb, low base. That comes over here on our acidotic side. So we get tic-tac-toe on the acidotic side, but this time it's our metabolic indicator that's over here with the pH. So I know that I have metabolic acidosis. Now take a look at your PCO2 value though, because it's not normal, it's pulling the opposite direction. So I can add that this has partial compensation. Again, the two systems are pulling opposite directions, but the pH is still abnormal. So that makes it partial compensation instead of full compensation. Okay, you try one. Pause the video for a minute. Make your tic-tac-toe board or use whatever system makes sense to you and see if you can figure out what this blood gas is showing us. Once you have figured it out, click play again and I'll show you my answer. Did you get respiratory alkalosis? If so, great job. If not, let's walk through it real quick. The pH, 7.48, that's high, that's alkalotic. So there's my pH. The PCO2 is 31, that's low. Low acid, that also is alkalotic. The PO2 is a little high. Maybe they're taking big deep breaths. And then the HCO3 is normal, right there in the normal column. So respiratory alkalosis, no compensation. This is what we call hyperventilation. If someone's in a lot of pain or they're really anxious or scared and they start to breathe too fast, too much, then they're breathing out too much carbon dioxide and they make their body alkalotic. So this is why we tell them to breathe into a paper bag, so they're actually rebreathing some of that exhaled carbon dioxide and they bring their pH back into normal ranges. Here's another example for you. Go ahead and give it a try. Push play when you're ready to see the answer. This one was a little tricky. So it is respiratory acidosis with full compensation, but let's walk through it together to make sure you understand why. So pH 7.36, that's normal. Great, hooray! But wait a minute, the other two indicators are not normal. So PCO2 of 50 is high, too much acid, that's acidotic. And then our bicarb 29, too much base, that's alkalotic. So what we have is our two indicators, our respiratory indicator and our metabolic indicator, pulling in opposite directions. So this is full compensation because the pH has ended up back in the normal range. So then how do I know whether it's respiratory acidosis or metabolic alkalosis that has been fully compensated? Well, I have two clues. First, the pH of 7.36 is just barely normal, but it's really close to being acidotic. So it could have been in the acidotic column with the respiratory indicator, giving me a clue that respiratory acidosis was the original problem. However, my other clue is clinical. I have a 3-year-old with infantile scoliosis. I know that that causes respiratory issues, so again, it was probably the respiratory problem that was the underlying cause. It's just been going on long enough that the metabolic system has been able to fully compensate. As we wrap up, if you're still feeling confused, don't get discouraged. Go back, watch the video again, try the practice problems again, and see how you make out. Also work on the worksheet that's due for homework. See how you make out there. If you're still having trouble, don't despair. We are going to go over this again in class together because it can be a tricky topic for a lot of people. When you're going back to review this stuff, make sure you first figure out what your normal values are. Remember, we have the respiratory system versus the metabolic system. Make sure you figure out the difference there. And then work on naming your blood gases. And then figuring out whether there's compensation or not. Good luck. Let me know if you have any questions while you're working.